Hi everyone, this is going to be a fast demonstration of doing code level ionization in ORCA using equation of motion coupled cluster method. So what you need, just a starting geometry. So here I'm taking I usually love doing test in water molecule. So here's I've taken a water molecule. This is a water molecule, and then what you need this input file. So if you're looking for this video over internet, then I assume that you know about ORCA and how its input file looks like. But here in this particular case of code level ionization, let's just have a look at the input file, and then we'll run a calculation which is very fast here because this is just a water molecule and a small basis set, and then we can see the result what we're actually planning to get, whether we're going to get that in the result or not. So let's have a look at the input. So this is how the input looks like. So the first line, so fix the basis set. Here I have taken the dep to SBPD. You can take even smaller basis set than this, like dep to SBP or something, just to make the calculation much more faster. But since this is water molecule, it completes in within few seconds. And the method, you specify the method which is IP-EOM-CCSD. Then the second line is actually very important. So because in ORCA it technically it takes it makes this frozen core by default. So if you want to compute the core IP or core ionization potential, you need to fix this line. You need to put this line in the input file, no frozen core. That is very important. And then these are CPU information, whether you are going to do a parallel calculation or running a calculation at a single CPU. Then from here, and this is the memory information. Then from this MDCI onwards, so these are the keywords related to the core level ionization calculation in ORCA. So we'll just see, we'll just quickly go through this. What are this? So this is basically when you run this code level ionization in using equation of motion coupled cluster. The approach they use this core valence separation. This basically like decouples the effect of the coupling between the valence and the core orbitals. That is very common approach. You can look over the internet. So this this CVS-ORV, so that actually starts with two numbers, one initial, one final. So what it means, so you need to, now here we are requesting for four roots. Four roots means so different ionization energies. Or four different ionations. So this is water molecule, and here we have five occupied orbitals, and here we are requesting for the four of them. And this CVS means, so this CVS ORB and this number of orbitals, this actually starts from 0 in this scheme. So this CVS orbs, this initial and the final, so this is the number of orbitals we are considering for the core valence. The orbital number we are considering for the core valence separation, that is initially 0 to 3. So these are the CVS, and then you need to make this following keywords true, just to enable the CVS scheme for the EOM-CCSD method. This is like this CV-SCP true, this do CVS true, and the do core true. With this do core true, this is directly targets the core orbital. And then one of the another important keyword here is core hole 0. So here we have only like water molecule, so the core case is only the oxygen 1s case. So here we are putting this core hole 0. So this core hole 0, this automatically starts from your like highest ionization potential value. For here it is starts from oxygen. But let's say you have like in a molecule you have two different atoms like carbon and oxygen, and you don't need the IP of the oxygen. Then in that case, what you could do, you could directly use use a number corresponding to the carbon atom, and that could like evaluate the ionization energy or core ionization energy of the carbon atom. So here in this case we don't need to do that because this is just simple water molecule, and the core level is only because of the oxygen bonus. And these are some printing level information, and this max iter. So basically for each root you need to fix a iteration and keep it like as much as possible, because for some of the roots it actually becomes complicated for convergence. And then next is XYZ file. Since I have this file struct.xyz, I can directly use this name, or you could directly paste this coordinates here directly. But when you go to the larger molecules, it becomes difficult, so it's better to always put your coordinates in a file and then just use that file. So this is all about the input file, and this also you can get from ORCA manual as well, and as well as from some ORCA discussion forum kind of thing. So now let's run a calculation, and this simple So this is submit script just to submit in a cluster, but this is the like this ORCA. You That's the keyword to run the job ORCA. Then your test file and whatever name you want to give to your output file. So let's run this calculation. It will not take like it will get completed within few seconds. So let's see. Yeah, I guess. Yeah, now you can see, so this calculations are completed, so you can go to the end line of the output file. This ORCA terminated normally. Then I'll not go over the output file in detail. Let's just go directly to the position where we're interested. Okay, this one. So this EOM-CCSD results. So we ask for like four routes. Now you can see route 1, route 2, route 3, route 4. Each of them are ionization from 0, like which is our core, then from 1, then from 2, then from 3. So and now these are the orbital energy. The oxygen one is core level, that is 543.673, and these are other three levels. If you request like 5, then you can get 5. If you request like 1, you can get also 1 route. So this is how you can do the core level ionization calculation in ORCA. This is very simple. So try this out and let me know if there are any problems in the comment section. Thanks for watching.